Okay, so let's now proceed on to, now that we've sort of warmed up with the whole concept of subgradients, let's actually now apply it to calculating the projection operator on the L1 ball. So, you notice that when right in the beginning, right here, this is where I ran into trouble. When I went to take grad of Lagrangian, I ran into grad of C. That's where the problem was. And so now I've built up one tool which is the sub differential, which is going to help me to actually work on this grad C. This is the whole reason why I did this business. Okay. So now let's go back to applying it. So maybe I'll just start from a new page. Okay. Okay. So in this case, y is the point that is fixed, or I can say it's given to us. Okay. And that is my constraint C of x, right. I am just rewriting what we have. So Lagrangian of this problem, what is the Lagrangian of this problem? I want to minimize this function y minus x whole squared, right, distance of my given point from any point in the feasible set, right. Is the geometry is clear? So if I were to plot it over here, this is my feasible set, right. This is my feasible set, and now I am giving you a point, let us say here, supposing this is my point y. I am asking you from this blue box, tell me the point which has the smallest distance, and here smallest distance is Euclidean distance 2 norm, because the definition of the projection operator does not change, that remains 2, right. So of all of these guys, tell me who's you know, for example, it might be some point over here. So tell me what this point is, question mark. Okay, that's what I want. So therefore the Lagrangian, what is the objective function? Mod, no. Why mod? Mod, we are not working with scalars anymore. Norm, L2 norm, right, half, because this, there was a 1 by 2 here, half of x minus y whole squared minus, now comes the Lagrangian, what do I write? 1 minus 1 norm of x, this is my Lagrangian. Okay. So now to apply KKT, I need to look at, that's how I wrote it, no, f of x minus lambda ICI. We are relaxing that now, right. The condition was that f and c should be continuously differentiable, if you remember in the KKT condition. Now we are going to relax that a little bit and see can it still work, right. Obviously if it were differentiable, then this problem would not be applicable over here. Okay, so first term derivative, gradient rather with respect to x, gradient of half x minus y whole squared with respect to x is, come on guys, right. You can just open it up, for example, right, x1 minus y1 whole squared plus x2, and take derivative and you will get this. Sorry, not the norm, what am I writing, you will just get this, right, it's a vector. Okay, then I have my issue over here, which is So this becomes a plus lambda, and I have, right. Is there any condition on the Lagrange multiplier as per KKT? Greater than or equal to 0. So we also have the complementarity conditions, which will say what? C1, there is no 1, so just Cx into lambda equal to 0, right. So if, let us take the simple case, if lambda equal to 0, that is a possibility. If lambda equal to 0, my gradient of the Lagrangian becomes very simple, right. That lambda term goes away. What do I have left? X minus y is equal to 0, implies what? X is equal, so this actually I should write this as x star, right, the best x, the solution to the problem. X star is equal to y. What does this correspond to? Right, that means, so very simply it means that C of x is either greater than 0 or equal to 0, which means where is the point? Where is the point y? Is already inside the blue box. So if I am asking you to project that point, I will get back that same point. So that is this point, right. So i.e. y was already in the feasible. Lambda equal to 0 means I'm using this over here. Just substituted blindly into this, right. The second term vanished, and I said gradient of Lagrangian equal to 0. I'm simply left with x star minus y equal to 0. No, I don't even need subgradient over here. Now second case is lambda not strictly not equal to 0. Therefore, what does it imply? Complementarity says that C of x has to be equal to 0. Okay. Okay, so I have now, so I need to worry about this guy. This is the term I need to worry, because now that term is not 0 in the Lagrangian, right. I need to worry about this term. Okay. So now I can open up this guy, right. I know this from the definition. Okay. Now when I start taking the derivative of this with respect to, when I take for example grad of Lagrangian, let us go back to first principles. What is gradient? When I take gradient, I am taking partial derivative with respect to x1, with respect to x2, with respect to each one of those guys. So let me take just the ith component of this. So I can write this as, this will be the ith component of grad Lagrangian, right. What all will it have? So I am asking you to write the ith component of this expression over here. The first term, what will it be? 1. Ith component of this, xi minus yi, obviously, no. Why will it be 1 or 0? Okay. Plus lambda. Okay. Remember, I am going to expand this 1 norm of x as sum of mod xi. Now, x1, x2, and I am taking derivative with respect to xi. Which term will survive? Only mod xi will survive, right. So this I am going to write as, whatever it is, it's going to be this, right. So it's a nice thing, because all the other xi's don't appear in this feature, because I'm taking derivative with respect to xi. So xj for j not equal to I don't appear in this expression. And what will I do? I'm going to set this equal to 0. That is the meaning. So what have I done? I've applied KKT. I've applied KKT with only one tiny difference. Instead of writing it as gradient, I'm writing it now as subdifferential. That's the only difference that has happened. Okay, so maybe we'll again go to the next page. Okay, I'll just rewrite this again on the top, xi minus yi plus lambda subdifferential xi equal to 0. So, as per KKT. Okay. Okay, so we can split this now, right? Because mod xi has trouble only at xi equal to 0. So, let us start with the easier cases. Supposing xi is greater than 0, then what happens? I am going to write this expression xi minus yi plus lambda into 1, right? When xi is positive, grad of mod x is 1 is equal to 0. Okay. Xi less than 0, this will still be xi minus yi, then plus lambda into minus 1 equal to 0, and xi equal to 0, same thing, xi minus yi plus lambda, and this is going to still be the subdifferential. What values can it take? Any value, right? Any value which is in my hand. Okay. So, I can just, looks a little messy, I can rewrite this in a nicer way. So, xi will be equal to yi minus lambda in this case, xi will be equal to yi plus lambda in this case, and xi will be equal to, this is example, right? So, I can take del xi is equal to 0. 0 is a candidate function, right? So, is there again a compact way to write these three things? Signum of simpler. Why is a signum of something? So, okay, so xi is equal to yi minus lambda into signum x. It works, right? When xi is positive, I have plus 1, xi is negative, I have minus 1, when xi is 0, I have 0. This is a candidate for a right, candidate. Why? Because I have taken a particular value of 0, it's perfectly legal. Okay. And I can just so this is what I get. Let's quickly recall, in this problem what is given to me, what do I have in hand, what do I know? So, there are three terms in this expression, x, y, lambda. What is lambda known to me? Other than the fact that it is in this case it is strictly greater than 0, I do not know what it is. Do I know what is xi? No. Do I know what is yi? Yes. So, I only know yi. So, we only know, and we have to somehow determine what, both xi, and you can see from this expression I need to know lambda lambda also, there is no lambda, I also need to know lambda. Okay. So, now let us try to make a little bit more progress. So, since we only know yi, what I will do is, let me sketch a number line with yi on it. Okay. Okay. Supposing I mark this as lambda and minus lambda over here. Okay. So, this thing can be rewritten as yi is equal to xi plus lambda. Okay. So, if yi is greater than lambda, okay, look at this expression over here. If yi is greater than lambda, it is compatible with what set of numbers for xi? Positive, right? So, over here this is xi greater than 0, right? If I am over here, where am I? Yi is less than minus lambda, xi is actually negative. right? We're just playing around with this expression by substituting different values, right? You can take either of these two expressions. When let's take this expression, right? You can substitute when you start with a value of yi equal to, let us say, 0, right? When yi is 0, what value will I get for xi? 0, right? When yi is 0, then I'm going to get, correct, it is consistent. If I substitute xi equal to 0, fine. Now when I start increasing yi, when yi goes past lambda, what happens? Then xi becomes xi equal to 0 is at the border of yi equal to lambda. Now as I start increasing x from here, right, it is consistent. So this is kind of the operation that is happening between x and y. There is it's interesting to plot it even further. Here we only plotted yi. Now let's actually do a simpler thing. Let's plot xi on one axis and yi on the other axis. This will give the full picture. So yi continues to be here and I'm going to plot xi over here. Okay. So when yi is, and let's keep these equations in mind, right? These are the equations to be kept in mind. When xi is greater than 0, we have xi is equal to yi minus lambda. That's the equation of a line. How does this line look like? Slope is going to be negative, positive, or what? Positive, right? So it's actually going to be right, because in this equation, what is the intercept? Minus lambda, right? Y is equal to mx plus c. M is 1, c is minus lambda, so it's down. Okay. Then let's take this equation. This has, what is the slope of this guy? 1. The slope is still 1, but intercept is plus lambda, right? So this is actually going to be like, I mean, drawing is not to scale, but basically something like this. Okay. Actually, this I'm going to leave it as this. Okay. In these equations, if xi is I mean, if yi is less than lambda, then xi equal to 0 is consistent, right? Do you see this? In this expression, if yi is less than lambda, what happens? What is the value of x that I can choose? 0 is the only thing that will work between lambda and minus lambda. Only one possible point, meaning? Correct. So this, so you're saying it's not the whole. Yeah, it will be like that. Because we chose signum. Okay. So this is how it, this is the relation between xi and yi. Okay. So let's continue building on this. So I'll try to write this in a even more compact way. Okay, if it helps. Yes. Yeah. I took differential as 0. That's why the signum function is floating around everywhere. It's not undefined. I've chosen the subdifferential to be 0. Hmm. 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 No, xi is yi according to that relation, right? Yeah, yeah. Yi is less than lambda. Yeah. So let's look at this expression, right? So if yi is less than lambda as per this relation, what do I get? Not, we can't determine xi from this. That's the point, right? That, yeah, that's precisely the point. I cannot determine xi from this expression if yi is less than lambda. If yi is greater than lambda, then yeah, but that's okay. We want to solve this problem, so we are picking signum of x to proceed with solving this problem. Okay. Okay. So now this expression that I have written over here for xi. Finally, remember we know yi and we want to solve for xi and lambda. That's what we want to do. So I want to rewrite this in a way that will help me a little bit more. So I'm going to write this as. Tell me if you agree. Basically, look at this graph, and we are trying to write this graph in a compact form. Okay. So if you look at this graph now, let's forget everything that we have done until here. Let's look at this graph. I want to write this graph in a compact form. So when yi is greater than lambda, what is the value of xi? I am reducing yi by lambda, right? And what am I? And the sign is positive. For example, when yi is greater than this. When yi is less than lambda, what happens? Again, the value of x is being chopped by lambda, but it's getting multiplied by a negative sign. So this expression over here, xi is sine of yi. So it will either plus or minus depending on whether yi is greater than lambda or less than lambda. And mod yi minus lambda is showing me the chopping that is happening over here. Graphically, I can see there is a chopping happening over here. But notice I have defined this plus over here. This is to take care of what? This issue when yi is between minus lambda and lambda si. So this is a well-known operator. This plus operator is simply, so if I write a over here, is this is the meaning of the plus operator. So if the argument is greater than equal to 0, then the operator spits out the same number. If it is less than 0, it spits out 0. So in layman's words, what would you call this? Thresholding. You just thresholds. If a number is greater than 0, or clipping, right? You're clipping a signal to not go negative, right? So this expression over here, it explains the graph. Right? Okay, so I've got this expression over here. I'm still not out of the woods, right? Because I want to be given the xi. The projection operation should give me xi, right? But I don't know xi, I don't know lambda. Okay, I've got a convenient expression. You notice that between this expression, let's call this expression b, and this expression, let's call this expression a. What is the advantage of expression b over expression a, or disadvantage of expression a over expression b? Exactly, right. In expression b, it's very neat because everything that I know is appearing on the right hand side. I can work with this. On the other hand, expression a, I have signum of xi, but I don't know xi to start with, right? And the unknown is appearing both on the left hand side and right hand side. That is, xi is appearing on the left, it's appearing on the right. So it's a clumsy thing. So all I did from that expression is to plot it. Plotting it, and then I rewrote it in this form, right? So what is happening in going from expression a to expression b is not algebra, it is sketching, or in other words, geometry. That's what has allowed us to go from expression a to expression b. So don't always rely on brute force algebraic symbol manipulation, as they call it, right? Sometimes just plotting it out shows you, oh, this is what it actually is. Now let's get, yeah, question. When, okay, so what happens when yi is between minus lambda and lambda? What happens to the plus operator? What will it spit out? 0, right? And that's what we have. So when I have one sec, so xi equal to 0 is happening for the entire minus lambda to lambda. For when yi is between minus lambda to lambda, I only get one value. That's like the signum function, right? But I don't want all the points. I am fixing it to be 0, which is 1, which is 0. Mm. No, okay, look at the signum function. Where's it going? Yeah. For the entire range of values, I'm only picking one number 0, right? It's not continuously varying. We can work it out, but I mean, you see, the signum function is picking one, right? So for the entire range, I'm forcing the function to take only one value of 0 rather than allowing the function to vary. That's the difference. But okay, we can work it out. By varying the subdifferential. But if I don't vary the subdifferential, correct. So if I don't vary it, supposing I fix it at 0, which, yeah, yes. Oh, for all the values. No, right? Because I'll only get xi equal to 0 no matter what value of y is between minus lambda and lambda. Which is true for all values of subdifferential. Is that true? So let's look at the general expression that we had, right? What was the general expression we had? Yeah, this, right? So we are looking at this expression, right? So this expression was written only at xi equal to 0, right? At xi equal to 0, you're right. That would happen only if the subdifferential basically mimicked the value of yi. There's a lambda missing over here. Yeah, correct. To maintain xi equal to 0, the subdifferential has to basically take the value from minus 1 to 1 as y is going from minus 1 to 1. Yeah. No, there's a lambda multiplying there. No? As y goes from minus lambda to lambda, subdifferential goes from minus 1 to 1. Therefore, xi equal to 0 remains xi equal to 0. Correct, you're right. So, the subdifferential tracks the value. So, this graph is also fine then. I mean, right, the graph is fine. Xi remains at 0 as yi goes from minus lambda to lambda. That's an interesting construction. So that's why to show it, that's why I erased the orange line connecting, right? It's just one point over here for the entire range from minus lambda to lambda, which is an unusual kind of a, you can't even draw it, right? Can you draw it? No, it is a line. Actually, it's correct then. Yeah, actually, so no matter what value yi takes between minus lambda and lambda, xi remains 0. So then that's a proper line. So I was right to begin with. That's good. Yeah. Okay. Right. So you notice this way of writing this graphical relation between xi and yi, particularly for those of you working on the course project, you may come across this operator many times. This is also called a soft thresholding operator. Okay.